Hey everyone, I am here to go over the CH1020 Exam II from spring 2018, and I want to go through the problems, kind of give you why the answers are what they are, kind of run through them, in hopes that you can use this video as a tool to study and to understand the concepts better. So with that being said, let's dive into reaction number one. So in this reaction, we're asked to predict the rate law for the overall reaction given a mechanism. And in this mechanism, you can see that there are two steps. One is slow, one is fast. That means we have to determine which one is really affecting the rate law. And it's going to always be the slow one. So imagine you are baking a cake. Well, first you got to make the cake batter. That might take somebody who's good at it 30 seconds, 2 minutes, whatever. And then you have to actually bake the cake, put it in the oven for 45 minutes. So when we ask how long does it take to bake a cake, you'll say, oh, about 47 minutes. Really, the majority of the rate at which you can bake a cake is dependent upon the slower of the two steps. So that's why we're going to base the rate law of this reaction on the slow step. So the rate for the slow reaction, as you can see here, is the slow reaction. And so the rate is equal to a rate constant times the concentration of those reactants, NO2 and O3, which is ozone. And so that is why the answer is A. So let me clear canvas. And let's talk about number 2. How many neutrons are produced when plutonium 239 plutonium is bombarded with alpha particles? So when something is said, when a problem says we're bombarded with blank, that means it's a reactant. So we know that we have a couple alpha particles, or exactly one alpha particle, on our reactant side. Well, when they react, it forms 240 Am, a proton, which has a mass number of 1 and a charge of 1. I'm just going to call it P, plus some mystery number of neutrons. And a neutron always has a charge of 0 and a mass number of 1. So, and let me write the charge or proton number of plutonium. So, when we have this nuclear reaction, we need to make sure that our charges are equivalent and our mass numbers are equivalent. Pretty much charge or energy and mass are both conserved. No matter what is on the reactant side, what's on the product side, they must equal each other. So, well, the mass numbers are already good. We have 96 on this side, 96 on this side. So that doesn't really help us with determining number of neutrons, which makes sense. Neutrons don't contribute to the proton number. But we can look at the mass numbers. So currently, we have 243 on this side, and we have 241 plus x times 1. I say 1 because there's always one mass number and a neutron. So we kind of just have to give it an equal sign and then solve for the correct number of x. So 243 equals 241 plus x. Well, that means 2 equals x. Therefore, we have 2 neutrons. And that is why the answer is C in this case. Right here. Cool. All right, let's talk about number 3. So we have all of these Ag things, and they're being dissociated into their ions. And so we're asked which one's going to give us the greatest concentration of Ag. And if you notice, Ag is always a product. And we have these differing number of Ks. Well, let's go over again what is K, our equilibrium constant. An equilibrium constant is this ratio of products over reactants once a reaction has reached equilibrium. So sometimes we call this KEQ, because there's a lot of K's in science. So we are looking on how K affects the concentration of products. Well, if we want more products, we want this numerator to be big and this denominator to be small. That's how fractions work. So in order to maximize our number of products, we want as big as a K value as possible. Well, looking at our K values, we see that K equals 1.52 times 10 to the negative 8 is the largest of the K values on here. So that is why when we start off with AgOH, we are going to get the largest amount of AgOH or Ag plus as we can possible. So the answer is going to be D. All right, so let's go on to question number 4. So for question number 4, we're asked, in general, as temperature of a reaction increases, so does the reaction rate. And then we were given these 4 statements, so we got to figure out which ones are true. Now first, in the kinetics chapter, we're given this equation. And we're told that the reaction rate is based off of this constant, Arrhenius's constant. I might be spelling that wrong, so forgive me. Based off of activation energy. This is a gas constant. And this is temperature. Temperature in Kelvin, if you had to put it in. Well, we're going to look at this equation and determine how changing temperature affects things. So statement number 1 says that by raising the temperature, the frequency of collisions increases at higher temperature. So let's think about it on an atomic level. We have a whole bunch of bouncy balls in a jar. That's kind of like atoms. Well, if all these atoms are moving faster, they're going to hit more often. Imagine kind of lukewarm shaking a mason jar filled with marbles, and then imagine shaking it vigorously. There's going to be more collisions when you move faster. So collision theory tells us that by increasing number of collisions and increasing concentration, we're going to get more reactions. That's because by increasing number of collisions, we're increasing the energy that each molecule has. The more energy it has, the more likely it's able to convert into a new molecule. Now, orientation, you see, it's like a key and a lock. These atoms, when they come together, need to have like the right orientation. If they don't, we're not going to get a new particle. And the way you make it more likely that they have the right concentration or orientation is to increase the concentration. So by increasing the frequency of collisions, this A increases. Therefore, K increases. Pretty much that's saying that statement 1 is true. So let's talk about statement number 2. Statement number 2 says the activation energy of a reaction decreases at higher temperature. Well, let's look at a reaction path, something like this. The activation energy is the energy difference between a reactant and the transition state. Transition state. And no matter what temperature this is at, or how cold it is, whatever, the reactants have a certain amount of energy in their chemical bonds, and the transition state have a certain amount of energy in their chemical bonds. Temperature doesn't affect how much energy is in a chemical bond. It affects how fast they're moving, but not the chemical bonds. So statement number 2 is false. Let's talk about statement number 3. The concentration of reactants increase at higher temperatures. Now, let's think about this on a macroscopic level. Let's say you have a glass of sweet tea. That's pretty sweet. If we put it in the fridge for 30 minutes, it gets colder. Is it any less sweet? If we leave it out in the sun and it heats up, is it any more sweet? No, there are still the same number of sugar particles in that glass of sweet tea. Therefore, temperature has nothing to do with concentration. Concentration would increase A, but temperature doesn't affect concentration. So this statement is false. Now let's talk about statement number 4. Statement number 4 says the fraction of molecules with adequate energy to react increases at a higher temperature. That is correct. That affects the increasing number of collisions, and these have more energy. It's like the marbles in the jar are moving faster. So this increases A, let me pick a different color, which increases K. So statement 1 and 4 are correct, and that is why the correct answer is going to be B, statement 1 and 4. All right, so let's talk about reaction or question number 5. So, 1 second. Cool. All right, so what is the correct equilibrium constant expression for this equilibrium? That just means we need the right expression. We don't need to solve anything. Well, we know that K is equal to products over reactants. And for Kc, it's concentration of reactant or products over reactant. But let's take a close look at this chemical reaction. We got calcium hydroxide in the solid state dissociates to form the calcium ion and 2 hydroxide ions. These are in the aqueous state. So this is a heterogeneous reaction. Pretty much, we have different phases going on. And when you have a solid in this reaction with aqueous things, solids don't affect the equilibrium constant at all. Doesn't matter their initial concentration at all. It has no effect on Kc. So Kc in this case is just the products over 1, because there are no reactants that affect the Kc. So we have Ca, 2 plus, and then we have OH minus. But let's look closely at this chemical reaction. It has a stoichiometric coefficient on the hydroxide, and that does affect Kc. So this needs to be squared. And since there's no stoichiometric coefficient in front of calcium, we assume there's a 1 there. So it's assumed that there's a 1 right here. But we don't actually have to write 1. And so that is why the correct answer is going to be E in this case. Cool. Well, I'm going to take a slight break, and then I'm going to come back and start on question number 6. For problem number 6, it asks, or it gives us, the energy profiles for the 4 different reactions are shown. Which of the reactions will have the largest rate constant? So, as we know, rate constant is equal to kind of this Arrhenius constant times E raised to the negative activation energy over RT. So, the difference between these 4 reactions, the main difference is the activation energies. That's what we're going to look at. So, an activation energy, as we said before, is how much energy it takes from the reactant to the peak of its reaction path. to this transition state. Transition state. So if we're looking for the smallest or largest rate constant, what are we going to do to EA? Well, since this is a negative, the smaller that EA is, the smaller, or excuse me, the larger that this whole constant is because of the negative sign. So if this is larger, then it makes K be larger because those two things are directly proportionate. So what you need to know, as activation energy goes down, rate constant goes up. So which will have the largest rate constant? Well, it's going to be C, the one with the smallest activation energy. All right, so for problem number 8, oh, excuse me, that was problem number 6. For problem number 7, let's look at it. So for the equilibrium, Kc equals 2, we have this reaction. We have, we can call this like white 2 plus B2 is in equilibrium with 2 WB. All right. So it asks, which of the following mixtures are at equilibrium? Well, first of all, we need to figure out, what does K mean? Well, K is the products over the reactants. So for this chemical reaction, the K is equal to WB and squared because of that stoichiometric coefficient over the concentration of the reactants, the white pair and the black pair. And we know that this needs to equal 2 for it to be at equilibrium. Well, let's look at that first mixture. That first mixture has 2 white blacks. It has 2 pairs of whites and 2 pairs of blacks. Well, that equals 4 over 4, which equals 1. Therefore, this is not at equilibrium. So we know that mixture 1 is not at equilibrium. Let's talk about mixture 2. Mixture 2, the K, or the Q, it would technically be called, because this is the quotient at any given time. Well, how many white blacks do we have in Q? It looks like we have 1, 2, 3, 4. So I'm going to put a 4 squared up top. How many white pairs do we have? 1, 2, 3. How many black pairs do we have? 1, 2. So this is equal to 16 over 6, which is not equal to 2, again. So it turns out that the correct answer for this is that D, neither mixture is at equilibrium. All right. So let's talk about problem number 8 now. Let's see. Okay. For which is the equilibrium constant Kc increased when the temperature is increased? So we're kind of thinking about Le Chatelier's principle here. And whenever I talk about Le Chatelier's principle, I imagine a fish tank. And this fish tank represents a chemical reaction. Here are the reactants, and here are the products. Well, let's for a second think about an endothermic reaction. Endothermic. Endo meaning in. So for an endothermic reaction, heat is a reactant. So if we are increasing the heat for an endothermic reaction, it's like we're putting more water in this side of the tank. Well, which direction is the water going to flow then? it's going to flow towards the products. So if products is increasing, and K is equal to products, Kc is equal to the concentration of products over concentration of reactants, then for an endothermic reaction, Kc is going to increase. All right, so it looks like for number one, or reaction number one, it will be true. Now, just to be safe, let's talk about why number two is incorrect. So, for an exothermic reaction, exothermic, exo meaning out, we have a product, we have the reactant on the left side, the product on the right side. We have some water. In this case, heat is a product. So if we increase the temperature outside, it's like we're dumping water on this side of the fish tank. Well, if that side of the fish tank is too high, that means the water is going to flow from the products to the reactants. So if reactants are going up, this is what K is. K is product over reactant again. If reactants are going up, it's actually causing Kc to go down. So this is not true for an exothermic reaction. So that is why the answer is going to be only statement one, or A. Let's talk about the next problem. Problem number 9. Okay. So, how many intermediates and catalysts are present in this following reaction? So, when we have a whole bunch of elementary steps, I like to divide everything into 4 categories. We have reactants, we have products, we have intermediates, we have catalysts. Those are the things that are going to be making up every element or compound in the elementary steps. So reactants are only found on reactant side, only found on R side. Products are only going to be found on the P side. Intermediates are first found on the product side, and then on a later reaction found on the reactant side. So first product, then reactant side. And catalyst is the other way. A catalyst will first show up on the reactant side, then it will show up again on the product side. Side. So let's look at this reaction. So H2SO4. We notice that it's not in the overall reaction. So that kind of gives us a hint that it might be a catalyst. Well, let's look for H2SO4 again. Turns out it is a catalyst because it first shows up on a reactant side and then a later step shows up on a product side. So one catalyst already is H2SO4. All right. Now we have these. Well, these are neither of the actual products. So let's look out for them again. So this ion, C2H5OH2, shows up right here. So at first it is a product, then a reactant. Well, that means, and let me make sure. Okay. That means if it shows up as a product and then a reactant, that this is an intermediate. So we're going to put the C2H5 OH2 plus. So that's one intermediate. Now, what else is happening? Well, this is a product and it doesn't show up as an overall product. So let's look for it on a reactant down further below. Well, we see it right here. HSO4 minus again. All right. So that means it shows up as a product and then as a reactant, that makes it another intermediate, HSO4 minus. All right, so let's look at reaction 2. We already know that this is a intermediate. Br minus, well, that's a reactant because it shows up in the overall reaction. Then we make C2H5Br, well, that's overall product. Then we make water. Water does not show up as an overall product. So it's kind of raising a red flag that it might be an intermediate. Turns out, yes, it is an intermediate because it shows up as a reactant in a further down step. So the last intermediate is going to be H2O. So we have one catalyst, we have 3 intermediates, which tells us that the answer to this is C, with 3 intermediates and 1 catalyst. All right, let's talk about question number 10. Clear canvas. I realized when originally recording number 10, I made a mistake. And so here's my second attempt at problem number 10. So we're asked, what is the equilibrium constant Kc at 25 degrees for the formation of nitrosol bromide or nitrocell? And we have a reaction, but then we're given the delta G formation of one reactant and one of the products. So in order to find, or in order to relate delta G and Kc, we know, or we're given the formula, delta G standard of the reaction is equal to negative RT ln Kc. Well, we need to figure out what, we need to figure out what delta G standard is equal to. And from the last unit, we know that delta G standard of a reaction is equal to the sum of delta G formations of the products times stoichiometric coefficient minus the sum of delta G formation of reactants times their stoichiometric coefficients. So we have 2NO plus Br2 is in equilibrium with 2NOBr. So that should be NO. Sorry, my stylus is messing up. So we know that the delta G of formation of NO is equal to 82.4. We know that the delta G formation of NOBr is equal to 87.6. Now, why were we not given the delta G formation of Br2? Well, it is in elemental form. And the change in free energy to take an element and change it into elemental form, aka no change at all, well, there's no change in free energy. So that's why this is equal to 0. So we're going to use this equation now. We know that delta G of this reaction, the standard reaction, is going to equal 2 times 87.6, because that's a product. That's the only product contributing. And then we're going to subtract 2 times 82.4, which is the only reactant contributing to the change in delta G, or the change of G. Same thing as delta G. So when we do this math, we get delta G reaction is equal to 10.4 kilojoules. And that's it. That's the unit. I was thinking about the unit. So now we're going to plug it into delta G reaction is equal to negative RT ln Kc. Well, let's do a little bit of messing around to get Kc by itself. Now, first thing we're going to do is divide both sides by negative RT. So we get delta G of the reaction over negative RT is equal to ln Kc. Now, how do we get rid of ln? We can't divide by ln. We need to raise both sides by the e. So we get e raised to the delta G reaction over negative RT is equal to Kc. So E, now we're going to actually plug in some numbers.
It's 6 o'clock.
Times 10.4 over negative. Now for delta G, we don't use the 0.08206 R value. We use 8.314. And then the temperature in Kelvin, well, we're told is 25 degrees Celsius. That makes it 298 Kelvin equals Kc. And I believe we plug in this number. Let me check my work. We get, I forgot. This is in kilojoules. So what we need to do is we need to multiply this by 1,000 to get it into joules, because this is in terms of joules. So we got E, raised to the 10,400 divided by 8.314298 equals Kc. So Kc equals 0.015. And that is why the answer is going to be A. Number 11. 11 asks, well, iodine 137 decays to form xenon 137, which then decays to form cesium. Let me pull up a periodic table. Cesium, Sc, 137. So what are the modes of the decay for these two reactions? Well, as we notice, the mass number stays the same. But what's happening to the proton number? The number of protons that iodine has is 53. The number of protons that xenon has is 54. And cesium, 55. So each time we are going up or gaining one proton. And again, we're gaining a proton. So, what is the type of decay where we gain a proton and that's it? Well, that will be beta decay. And it's good to know for beta decay, we're gaining one proton by sacrificing a neutron. And electron capture / positron emission, we are sacrificing a proton in order to gain a neutron. All right, so we know that beta decay is true for both of them because from iodine to xenon to cesium, we're gaining a proton. And that's how you know. So let's talk about 12 real quick. All chemical systems at equilibrium must blank. Well, we can be at equilibrium and not have similar reactants or products. In fact, they could be very different. So we know that KEQ, products and reactants, we know this. Well, it doesn't have to be that products equal reactants. For most cases, that is not true. So we know that, let's say they're equal to each other, 2/2. If they were, well, that would mean that KEQ is equal to 1, which doesn't have to be the case, and that they don't have to be equal. So we can already get rid of A and B. Well, we know that KEQ is equal to the rate going forward over the rate going in the reverse direction. So when we're at equilibrium, we're saying that the rates are the same. We have the same amount of products that are turning into reactants as we do reactants turning into products. That's what equilibrium is. For example, we can talk about equilibrium in other ways. Remember our last unit when we talked about osmotic pressure. Well, it reaches equilibrium when the side with the solutes and the side with the solvent are going at each other at the same rate. In physics, something is at equilibrium if the force in one direction is equal to the force in the other direction. So that is what we get, that the rates are equal to each other. And so that is why the answer is going to be C, that the rate of the forward reaction equals the rate of the reverse reaction. It's not that the rate constants are equal to each other. Sweet. I'm going to take a little break, and then we are going to come back to question 13. Problem 13 asks, which of the following is the correct relationship between Kc and Kp of the following reaction? So we have this reaction. There's a couple of solids, gases, and gases. So first of all, we got to think about what is really affecting the equilibrium constant in this case. Well, due to the fact that we have solids and gases, solids don't contribute to the equilibrium constant at all. So we're really just focused in on the gases. And we also know that Kp is equal to Kc times RT times the change in moles. And this is change in moles not of everything, but of things that affect Kp, which can only be gases. Kp is the equilibrium constant based on partial pressures. The only phase that has partial pressures are gases. Excuse me. So this is change in gas only. So we need to think about how many moles of gas are on the reactant side, 0, and how many moles of gas are on the product side, 4 and 1. So we have a total change of 5. And that is why when we go from 0 to 5, we have a delta N equals 5. And that is why answer D is the correct answer. For problem number 14, there's a couple of ways to approach this. Now, the way I would do it is focus in on a molecule or a particle. And then some problems will ask you, well, there's 2 kilograms of cobalt. At the end, I convert it to a macro scale. So let's look at the individual level. We're producing a cobalt 59. Well, cobalt has 27 protons. I'm double checking that. Yes. So we aren't told what's the mass of a single proton, single electron, single neutron, but we still got to figure it out. So in cobalt, we know that there are 27 protons because of the atomic number. That means there's also 27 electrons because this is a neutral compound. That's the word. And then to figure out how many neutrons, well, it's the difference between the atomic number and the mass number. That's 32 neutrons. But what are the components that make up this molecule? We're only told about, let's see, the mass of a 1,1H and the mass of a neutron. Well, what's in a 1,1H? That's just a hydrogen atom that has a single proton and a single electron. So when we have H11 over here, how many hydrogens must there be to equal 27 protons and 27 electrons? Well, it's going to be 27. And then we're asked about neutrons. Well, we need 32 neutrons. So this is kind of the reaction that we're theoretically putting together. So what we're going to do is we're going to find the mass of this, and then we're told the mass of this, and we can find the mass defect, the change in mass. The mass of a single hydrogen is said to be, oh, I have it somewhere, yeah, 1.000783. And when we multiply that together, we get 27.2114. Should be a 7. And we have 32 neutrons. And a single neutron is 1.00866. So when we multiply that out, the mass of 32 neutrons, that will be 32.2771. That should be a 4. So when we take the sum of these two values, we get 59.4885. And then we're going to subtract the mass of the cobalt. And we're told that the mass of a single cobalt is 58.933189. So we take the difference, we get 0.555332 AMUs. Now, that's the mass defect of a single particle. So I'm going to write per particle to remind us, because we're going to do some unit conversions, but we got to keep track of everything, because we're not told that a single particle, or we're not asked the nuclear binding energy of a single particle, we're asked of 1 mole of cobalt. So we have 0.555332 AMUs of mass defect per particle cobalt. Well, it's good to know that 1 AMU of mass defect equals 1.493 times 10 to the negative 10th joules of energy. That's how much energy it takes, or is given to nuclear binding energy for every 1 AMU of mass defect. So AMUs cancel out. So at this point, we have joules of energy for every AMU, or for this many AMUs. But we don't want just 1 particle, we want 1 mole. So let's convert particles into moles. Well, we're going to get rid of particles, and we're introducing moles. So 1 mole is equal to 6.022 times 10 to the 23rd particles, right? So now we have the joules per mole. And there's only 1 mole, so this is actually going to be our answer. So if we plug that into our calculators, we should get, I wrote this down earlier, 4.991 times 10 to the 13th joules. That's how much energy it takes to bind this nucleus, aka the nuclear binding energy. So the answer for this is going to be B. All right, so let's talk about 15. 15, when they're asking for equilibrium concentration of this mixture, we know this is going to be an ice table, and we're going to have to solve for X. So we have this chemical reaction. Cobalt reacts with CF4, and it's in equilibrium with 2COF2. Well, we know the initial concentration. We can figure out kind of change in equilibrium. So we're told we initially have 5.00 here, 5.00 here, and we're told we have 1 molar of the product already. So at this point, we don't know which way, if that's where the question ended, we don't know which way this reaction is going. So it'd be kind of ambiguous, and we'd kind of be at a dead end. We'd have to solve it 2 ways. But we're told that the forward reaction is favored. So we know that means the number of reactions are going to go down, and the number of products are going to go up, which is fairly normal for ice table. So we don't know how much is changing, but since CO2 is a reactant, it's negative, and the stoichiometric coefficient is 1. So it's negative X. Same thing for CF4. Now, COF2 is a product, so it's plus, and then look at the stoichiometric coefficient. For every 1 mole of CO2 that's consumed, 2 moles of COF2 are produced. So that's why this change is twice as large. So our equilibrium values are 5.00 minus X, 5.00 minus X, and 1.00 plus 2X. Now, we know what Kc is in this problem. Kc is equal to 0.5. So we know that 0.500 is equal to this term. So 1.00 plus, plus 2x. Now, you'll notice I'm squaring this. All right, I'm squaring it. So the 2 stoichiometric coefficient affects it twice. Kind of as the change, it affects that, but also affects the Kc expression. So that's important to keep track of. And then we have 5.00 minus X. And then we have it again for the CF4, 5.00 minus X. So for those of you who are afraid of algebra, this is kind of looking scary because it looks like we're going to have some x squares, which means the quadratic formula. But don't dive in yet. There is a way to help you with this problem. Let's think about this. 0.5, sorry about my tablet, is equal to 1.00 plus 2x squared. And since these two terms are being multiplied by each other and are the same thing, they're both, the denominator is just one of those terms squared. So we can rewrite it as 5.00 minus x squared. All right. Well, if it's squared in the numerator, squared in the denominator, that means the whole fraction is squared. So if we take the square root of both sides, all of a sudden we don't have x squareds, no quadratic equation. And that equals 0.707 equals 1.00 plus 2x over 5.00 minus x. All right, so now it's just a little bit of algebra. We're going to multiply both sides by this, and we get 0.707 times 5.00 minus x equals 1.00 plus 2x. So we distribute out, we get 3.54 minus 0.707x equals 1.00 plus 2x. And then we get terms on the right side. We get 2.54 equals 2.707x. And then we divide both sides by 2.707. 2.707. We're left with 0.9367 equals x. Now, we're asked to find the equilibrium concentration of COF2. Now, that's not the same thing as x. What is the equilibrium expression for COF2? It's 1 plus 2x. So at this point, 1 plus 2x is equal to 1 plus 2 times 0.9367. And if we do that math right, we get 2.87 molar. And that is why the answer is going to be E, which is the closest thing. So let's talk about 16. Positron emission results in the change in an atom's identity. So you need to think about what is happening in positron emission. Well, you think about as a neutron. This is a neutron. A neutron is, if we look at the masses, it really turns out that it's made of an electron and a proton. So when we're able to bring in an electron, which is the same thing as electron capture and positron emission, it's like we are forcing the reaction in this way. So for positron emission / electron capture, we are sacrificing a proton and gaining a neutron. And the opposite is true for beta decay. We're taking a neutron, we're pushing it into a proton. So we would expect to see a decrease in the atom's protons and an increase in the atom's neutrons. So that's why 2 and 3 are correct. So the answer to this is going to be C. All right, let's go on, keep on going to question 17. Question 17 asks, nitrogen dioxide reacts with fluorine, and we have these 2 steps in this reaction path. Well, I want to kind of roughly draw the reaction path. Okay. So we need to figure out what's the which step is the rate determining step. Pretty much which one's slower. Is it going to be step 1 or step 2? And the way we use this graph is whichever reaction, this like hump, has the biggest activation energy, is going to be the slower step. So this hump starts from this line and goes to the peak of this. So that's how much activation energy it takes for step number 1. Now step number 2 starts right here and only goes up a little bit. Okay? So that means activation energy of step 1 is a lot larger. So that's the rate determining step. So if we base the rate law on the rate determining step, we get that the rate is equal to K times the concentration of NO2 and F2. And this is okay because both of these are true reactants and not intermediates. So we don't need to change anything, and that is why the answer to this is A. Cool. So let's do 18. And I feel like these diagram ones trick up a lot of people, but it's usually as simple as counting up things. So let's think about what is decaying in this case, and what is it decaying into. For this initial diagram, we have a lot of white dots, and we have less over here. That means white is decaying. So that's the first thing you need to understand. Now, let's count how many whites there are initially. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 initially, and 1, 2, 3 after 60 years. So our initial amount is 9. Our amount at t equals 3. Our time equals 60 years. And with the integrated rate law, we know that the natural log of AO over AT over K equals time. Well, we know these three, so we're going to use this to find K. So ln AO over AT over T equals K. And that is ln of 9 over 3 over 60 equals K. And K in this case equals, let me see, I have it written down. .0183, and it's going to be 1 over years. Usually, for half-life, the unit is going to be 1 over time. In this case, we see 60 years is the time we're using, so we're keeping with that unit. So now that we know the K, the rate constant, we can plug into the half-life formula. And the half-life formula is that the ln2 over K is equal to the half-life. So all we're going to do is ln2 over 0.0183 equals half-life. And that is equal to, I believe, let's see. In my calculator, I got 37.8558 years. And that's going to be closest to answer C. So the answer in this case is going to be C. I'm going to take another quick break, and I'll come back. For problem number 19, we have a reversible reaction of X2Y4, that's in the gas phase, is in equilibrium with two XY2s. And this has an equilibrium constant of 2. Which means that Kc is equal to xy2 squared over x2y4. And that's equal to 2. So which direction will the following reaction mixture proceed when reaching equilibrium? Well, we got to look at this diagram and see what Q is. Pretty much, what is the ratio of products to reactants currently? Probably not at equilibrium. Well, from looking at this, I see 1, 2, 3, 4 XY2s. 4, so that's up top. Then we have 1, 2, 3, 4, 5, 6 X2Y4s. So that's 16 over 6. That's, let's see, I can't do the math. Clear, 16 divided by 6, it's about 2.66, which means that, and let me make sure I got that math right. This is problem 19. It means that Q is going to be greater than Kc. And if Q is greater than Kc, then we know that this reaction is moving towards the left. It's going to favor the reactants. So that lets us know that this reaction will proceed to the left until the reactant sides meet equilibrium. So that's B. All right, clear canvas. A catalyst speeds up a reaction by blank. Well, let's go through each of these statements. Providing a rate determining step with a smaller activation energy for the reaction. Well, yeah, that's what a catalyst does. It speeds up the slowest or the largest activation energy. So number 1 is correct. Number 2, is it going to provide a larger rate constant for the reaction? Well, we know rate constant is equal to A e to the negative EA over RT. So if we put in a catalyst, we're decreasing the activation energy, which shoots K up. So we know statement number 2 is correct. Now let's talk about statement number 3. Providing an alternative molecular pathway for the reaction. That is true. So let's say we have a normal reaction that looks like this. When we add a catalyst, usually it kind of breaks it up into 2 steps, but it always lowers the activation energy. It goes something like that. So this activation energy, I'm going to put it to right here, activation energy is much smaller than that large activation energy. So statement number 3, well, let's see, it's a different path because we haven't hit the same transition states. So therefore, statement number 3 is correct, and 1, 2, and 3 are correct, so we're going to select answer E. Let's double check to make sure. Right. All right. So for 21, we're saying that there's something about Earth's crust, stars, whatever. Well, what's important to note is that we're talking about Al26. That's decaying to Mg26. Now, according to our periodic table, Al has an atomic number of 13. Magnesium has a atomic number of 12. So what does that tell us? That this reaction is sacrificing a proton in order to gain a neutron. And that is positron emission / electron capture. So the answer to this is D. All right, let's talk about question 22. So consider the following spontaneous reaction, which means if it's spontaneous, it's going to go to the products. Which combination of concentration will lead to the strongest driving force for the forward reaction? Most negative delta G. So the thing that drives to the right most, let's talk about Le Chatelier's principle for a second. Now we could plug this straight into this formula, delta G is equal to delta G prime plus RT ln Q. And we can figure out, well, what combination does what to Q, and what does Q do to delta G? But I'm just going to think about Le Chatelier's principle. Think about like you have a fish tank. What is going to drive the water to go to the product side the most? Well, if we put in water into this side, into the reactant side, and we take water out from the product side of the fish tank, the water is going to have to keep on flowing to the right, which is what we want. It'll be the strongest driving force forward. So we're looking for the to maximize our amount of reactants and minimize our number of products? Well, that is going to be B. 2 molar of our reactant and 1 molar of our product. That is maximizing reactant, minimizing product. So that'll be B. Let's double check that. Yeah, good. All right, so for 23 is more or less Chatelier's principle. Now, we have this reaction. Copper, which is a solid, that's important, plus 2 moles of hydrogen gas goes to form methane gas. All right, and it lets us know that delta H, is negative. This number doesn't matter. What matters is that it's negative, also known as exothermic. So let's talk about adding more C. Well, does C affect the Kc expression at all? No, it's a solid. Solids do not contribute to the driving force of a reaction. So statement number 1 is incorrect. So let's talk about adding more pressure. If we notice, we have 2 moles of gas on this side and 1 mole of gas on the right. So naturally, the 1 mole of gas wants to take up less space. So if we're adding more pressure, the gas wants to condense. Well, which direction of the equation, a reaction will help it condense more? If more of it is forced to methane. So statement number 2 is correct. By adding more pressure, we're forcing it to condense to methane. All right, now statement number 3. Let's bring up the fish tank analogy again. Now for an exothermic reaction, we know it's exothermic because delta H is negative. Heat is more of a product. So I misread the problem. We are increasing the volume, which is the opposite of increasing the pressure. We know that from ideal gas law. Pretty much, if pressure goes up, volume comes down, they're inversely related. So their effects are going to be opposite. So since increase in pressure forced it to methane, more volume to spread out, well then we're going to go backwards to hydrogen gas because there's more room. So statement number 3 is incorrect. Sorry about bringing up exothermic for this endothermic. So the only one that is correct is going to be B, statement number 2. Now let's talk about question number 24. We have a whole bunch of randomness thrown in there that's meant to confuse you. Well, let's pick out what's the most important thing. We're talking about C14. A freshly cut piece of papyrus has 213 disintegrations per second. So that's going to be, and let me make sure I have this down right. That is going to kind of act as our AO in this case. That's how many disintegrations that this old piece of papyrus had originally. So that's why it's AO. Now, we look at this old scroll and see how many disintegrations it has currently. Well, that's 181 AT. And then we know that the half-life of carbon-14 is equal to 5730 years. We're going to use this to figure out the rate constant, and then use this to figure out T. So rate constant, when you have the half-life, falls in this formula. Well, you can switch these places, and K is equal to ln of 2 over half-life. And let me figure that out real quick. I'm plugging in ln 2 divided by 5730, and I get 0.000121, 1 over years for K. So then I'm going to plug it into our integrated rate law. Well, ln of AO over AT divided by K equals how much time has elapsed. Well, we know that our AO, we're going to call it ln 231,181 over our K that we just calculated, 0.0121 equals how much time has elapsed. So I'm playing my calculator, 231, ln of 231 divided by 181, make sure I'm doing all the values right, divided by 0.000121, and I get time is equal to 2016 years. So that will be closest to A, something that happened 2,000 years ago. And let me double check. Yeah, good. So for 25, nitrogen with partial pressure of that. So let's say the partial pressure of nitrogen gas is equal to 0.43. Partial pressure of hydrogen is 1.55. This is ATMs, by the way. And then we're at 500 degrees Kelvin. I don't think that really matters. When the system reaches equilibrium, the partial pressure of nitrogen has dropped to 0.32. So we're saying that the partial pressure of N2 at equilibrium equals 0.23 atm. And this, with the chemical equation, will give us enough information to figure everything out, to figure out Kp. 2NH3. And all these are gases, so all of them affect Kp. So initially, we're given these initial values, 0.43, 1.55, and since we weren't told the initial amount of ammonia, we're going to assume it's 0. Well, change, we don't know it yet, but the one other thing we do know is 0.23 is right here. So we can figure out the change. Well, initially it had this, at equilibrium it had this. The difference is negative 0.2 atm. So that's how much has changed. Well, if for every 1 mole of nitrogen we lose 0.2 atmospheres, that means for every 3 moles of hydrogen we lose 0.6 atms. And for every 2 moles of ammonia, which is a product, so we're gaining, plus 0.4. So that means that we have 0.95 atmospheres right here, and 0.40 atmospheres right here. Well, Kp is going to equal the partial pressure of nitrogen or ammonia, but you can't forget to square it due to the stoichiometric coefficient. And then it's going to be over the equilibrium partial pressure of nitrogen, which is 0.23. And then we have 0.95, but this is raised to the third. Let me double check. Good. So if you plug it all into your calculator, we should get 0.81. And that is why the answer is E. I'm going to take a break and come back to 26. So for problem 26, we have this reaction and we have a couple of different experiments. And these experiments are going to help us determine the order of the rate law in terms of X and in terms of Y. So for experiment number one, rate equals 1, and we have 2 X's and 2 Y's. Now let's look at experiment number 2. The rate doubles to 2. Now our number of Y's stays constant, but our number of X's doubles. Since this doubles and this doubles, and they increase at the same rate, then we know that X is first order. First order. All right, we can do the same thing from experiment 1 to experiment 3. I picked those because something remains constant. And so we need at least one of the concentrations to remain constant. So experiment 1, we have rate equals 1, 2 X's, and 2 Y's. For experiment number 3, rate is now 3. Our number of X's remain at 2, but our number of Y's triples to 6. And since our concentration of Y's triple and our rate triples, it's a linear, it's like a linear relationship, which means that it's in first order. First order means linear. Zero order means it's flat. Second order means like parabola. All right. So we know that the rate is going to be equal to some rate constant times the concentration of X to the first power times the concentration of Y to the first power. So reaction mechanism A. Let's look at this. All right. Well, there's only one step, so it's really easy to determine. The one and only step is the rate determining step. And that would mean that the rate is equal to kx squared y. Because in these mechanisms, the coefficient is the order. So this suggests that it's second order, so A is not correct. Now let's talk about B. B, the slow step, doesn't have any intermediates in it. It has X and Y, which matches the overall reaction. So it's as simple as writing down the rate law for the rate determining step. And according to B, the rate law would be K times the concentration of X and the concentration of Y. And that matches what we figured out from the experiments. Now, just for extra practice, let's go through C and D and explain why they are not true. So for C, our slow step is right here. So we have a rate determining step. And so for C, the rate is equal to kx squared. That is not correct. And D is the weird one. We have a rate determining step right here, but there's a problem. We have xy as one of our reactants, and that is an intermediate. I know it's an intermediate because it doesn't happen in the overall reaction. And we can't keep rate laws as in terms of intermediates. And so it takes a little bit of work. But we get that the rate is equal to k xy times x. All right, so we need to substitute in something for right here. We're going to use something called pre-equilibrium approximation. there's a red flag, or not a red flag, just a flag to let you know that you're probably going to have to do pre-equilibrium approximation. If the first step of a mechanism, or the fast step of a mechanism at equilibrium comes before the rate determining step, because that usually means there's an intermediate in the rate determining step. So we're going to write out this, and at equilibrium, the rate going forward and the rate going backwards are the same. So we know that the rate, or I'm going to go ahead and give the rate K1 of x, y is equal to the inverse rate constant. So that's why I'm calling this K1, still a constant, xy. So if I solve for xy, I'm going to divide both sides by k negative 1, and I get K1 over k negative 1 x y is equal to xy. So I'm going to plug that in up here, and I get, after I plug it in, rate is equal to k1 over k negative 1. A constant times a fraction of two constants is still called a constant. So it comes out to k. But I have x, y, x. So the rate from D is constant times x squared y. And this does not match, this does not match the rate constant or the rate law that we got from the experiments. So that is why the answer should be B. Cool. And that is all of it. I hope this helps.